Those of you who have found the practice midterm online and have started taking a look at it and giving it a shot, I wanted to um, provide a little bit of a video presentation here going over some of the solutions to those, so you have a little bit of extra help in case you can't come to office hours to go over the practice midterm. So I'm just going to go through one by one each question, give you a chance to take a look at it if you haven't taken a deep look at the actual practice midterm that's posted online, and then go over the solutions. So, first question, multiple choice, circle the answer that best completes the statement. In the most general sense, models are useful because they A, are highly accurate description of real systems, B, provide precise quantitative predictions about the trajectory of systems, C, provide insightful possible answers to what-if questions, and D, require no background in mathematics to use or understand. Now, say most general, then a red flag on A and B is that these don't sound very general. So for B, provide precise quantitative predictions about the trajectory of systems. Well, we've talked about mental models and qualitative models, so those are still models, even though they don't provide quantitative predictions. They might only provide qualitative predictions. By qualitative predictions, I mean a mental model might tell you that as the temperature goes up, then maybe the amount of sunburn might also go up, but you don't exactly know how much sunburn will go up. And then highly accurate descriptions of real systems, again, so a mental model is not necessarily highly accurate. There are certainly models that are highly accurate, but not all models have to be highly accurate descriptions. And D, require no background in mathematics to use or understand. That is also not a very general question. And so there are plenty of models like qualitative models or models that are, pictures and figures and things like that that don't require mathematics to understand. But there are models that do require mathematics to understand. So that's not a very general statement as well. So the most general statement that applies to basically all models is C. Models provide insightful possible answers to what-if questions. That's really sort of how we define a model in this class. Does it help us answer a what-if question about the world? All right, choose the answer that's incorrect. Sector maps are simplified versions of stock and flow diagrams used to better illustrate major system components or help organize the process of designing large, complex stock and flow diagrams. That statement to me actually seems correct, so there's no red flags there. B, a simulation time increment, or a DT, is not explicitly part of a stock and flow diagram, but it must be incorporated into a computer simulation to make predictions of the trajectory over time. That also seems correct to me. We've talked about the DT and how we don't draw it in as a stock and flow, but we do put it in a spreadsheet, so that seems good to me. C, flows represent the ways in which stocks change over time. That also sounds right to me. We say stocks are the state variables. They are currently how things are set in a system, and flows are how they change. D, stocks are also known as levels or state variables, and the value of a stock at any given time is sometimes known as its state. That also sounds right to me. All those things are correct statements. So I'm left with causal loop diagrams always include loops. Now, for the uninitiated, it might sound like a causal loop diagram would always have a loop in it because it is a causal loop diagram. But it is a causal loop diagram not because it has a loop, because it helps us find loops. So we go through the effort of drawing a causal loop diagram in order to find loops. That's where they get the name, causal loop diagram. So that is an incorrect statement. A causal loop diagram does not necessarily have a loop. All right, next multiple choice. System dynamics modelers operate under the assumption that the important features of a system come from the interconnection of components within the system, and the system's behavior over time is not random, but will behave according to patterns predictable from those interconnections. What is a name we use to describe this perspective? So we have talked about this perspective where you don't need randomness, where all of the dynamics come from just knowing the basic interconnections of all the components that we're modeling. And that is what we call the endogenous perspective, where everything comes from within. So it's not the event scheduling worldview we haven't actually brought that up in this class, although that is a simulation-related term, but it's for a different type of simulation. The Newtonian gambit, well, I just made that up. And then, naive. Well, it may be naive to make those assumptions, but hopefully we've built a model whose boundaries are wide enough that we're capturing kind of the salient features of the system, and we don't need to invoke, either external forces or internal randomness. So we're taking the endogenous perspective when we think that we can grow the boundary large enough to capture all of the important dynamics inside those boundaries of the model. All right, almost done with these multiple choice questions, but 4, a tool developed explicitly for representing the qualitative dependencies between important variables is a. If we look through this, let me say, well, a stock and flow diagram, although there are connections between elements that are depicted in a stock and flow diagram, a stock and flow diagram gives us quantitative predictions of what's going to happen in a system. And so it's not just there to represent the qualitative dependencies, it's actually there to simulate the system quantitatively. Similarly, a differential equation is a mathematical model which is quantitative. It makes numerical predictions. A spreadsheet is another tool that makes numerical predictions just the same way as a stock and flow diagram or a differential equation does. So you put formulas in a spreadsheet and it gives you numbers out. So the only one here that's really qualitative is this causal loop diagram, where you can't run a causal loop diagram, you can't solve a causal loop diagram, but in the process of drawing a causal loop diagram, sometimes you observe loops, and those loops and patterns of loops can tell you something about the system, qualitative things about what you might expect the system to roughly do, even though you don't know what it exactly will do. All right, question 5. Which of the following is most likely describing a flow in the stock and flow model? All right, so the key here is we see flow. Now we know that flows are rates. And so we don't know what stock this flow is connected to, so we have to make some guesses when we look at these answers here. But we know that we're looking for a rate. And so a rate is typically going to be per unit time. It's going to be like apples per second or people per year. So when I look at these things, number of police on the streets, there's nothing rate about that. That sounds like a stock. That sounds like it has a state variable. It tells me how many police are on the streets right now. Drugs available is another one that again sounds like a state variable, a stock. Time required to train an officer doesn't sound like a stock, but it sounds like a parameter. It sounds like it's not necessarily a rate, but it's a time that's associated with an individual officer in a model of, say, police. And so it is not describing a flow, although it might be used to define the formula for a flow. So all that I'm left with here is number of new police per month. And that per month is a rate. And so that's really what the key thing that you're supposed to be looking for there. Number of new police, that sounds like something that could be the units of a stock, and then per month is the rate part of it. All right, so now we get into a little more complicated one. And so this is getting more advanced. This is more like something that we'll see after the midterm, but I wanted to give it here because you might expect to see something simpler than this on a midterm, but still in the spirit of this. And then it's sort of a good example of where things are going. All right, so here's the scenario. You're modeling the population dynamics of waterfowl that reproduce sexually. So far I've only talked about asexual reproduction in class. So you want to model the number of males in the population separately from females. And so you create two state variables, M for males and F for females. Observing the population, you notice that any random pair of a male and a female will encounter each other every R time units on average. So before we would say that maybe each individually asexual bird might reproduce every R time units. Well, now we're saying, well, every bird, every male will have an opportunity, each male will have an opportunity to find some other female every R time units. And then, so then that happens, and then successful mating occurs only some fraction p of the time, and then that successful mating is only going to result in a male half of those times. Assuming that males have a lifespan of L time units and are immediately able to mate after being born, which of the following expressions might represent the net inflow of males in the population? So we're sort of modeling dm dt. So we're modeling the flow into the males stock here. Now, this is more complicated than we're used to seeing, but there are some things that look familiar, like this male lifespan. So we know that if males have a lifespan of L time units, we're sort of used to these population examples where the outflow from the population is just the number of individuals in the population divided by the lifespan. So if I look at that, I see 3 of these all have a minus m over L. So they all have this outflow that's consistent with what we expect with this L lifetime units. But this other one here has an M times L. So that tells me that C is probably not the right one. So then I have to go and look for other clues. And so here's this, in this kind of purple text, I see that any random pair of a male and female interact, they encounter each other every R time units on average, and then have a successful mating p proportion of the time, after which only half of those end up going to be male and will contribute to the male stock. Well, if I look at these 4 different options here, A, B, and, well, I guess C I've already excluded, so A, B, and D, these 3 options, I don't see P show up in B at all, so that's probably not right. Because it seems like P is probably important if only P proportion of the encounters actually result in mating events. And then the half of the time, well, that kind of makes it sound like I want to take the P proportion and divide it by 2, which points me only to this one here. So then if I look at this top line, then it starts making a little more sense. I'm saying that how many pairs of males and females do I have? Well, there's M times F pairs of males and females. And so those pairs almost become like the new population unit. So you're saying of all those pairs, how often does any one of those pairs actually reproduce? Well, that happens every R time units. So it's like we have an inflow of M times F divided by R. But of all of those new potential offspring, they only actually happen P proportion of the time, and then of those, only half of them are male, and so that's where we get the P over 2. So in the end, that ends up being the right answer because it has all of those components in it. So that's a little more advanced one, but if you can try to follow your way through it, I think you'll be in pretty good shape for the midterm, and I also think you'll be well anticipating some of the more advanced examples we'll see after the midterm, like in the SIR models and the other ones that we talk about. All right, now a CLD problem. So we got this CLD, which is sort of modeling sales growth and hiring in sort of a sales company, a company that does sales, a business. And so we have 2 questions. How do the hiring control departures and saturate loops modulate sales over time? So these are the loops: sales growth, hiring control, saturation, and then sales growth over time here. So, so this is this sales growth here. And so we're kind of interested in knowing how these loops interact and affect this growth here. So we can see all these things that participate in sales growth, like widget sales, annual revenues, and so on. So long as this curve is, or this loop is running, then widget sales will be increasing, and revenues will be increasing, and the sales department budget will be increasing, and the budget number of new people will be increasing, and so on and so forth. And so this giant loop here is going to keep growing and growing and growing, but then these loops interact with it. Then the other thing, draw an example of the behavior over time plot for annual revenues. Well, that's this dynamic variable right here, annual revenues. So let's handle the first one. How do these 3 loops modulate sales growth over time? Well, if we look closely here, we can see that I have this reinforcing loop next to a balancing loop, a positive loop next to a negative loop. So both of these hiring control Departures, oh, that's one that I missed a second ago, and saturation. These are three negative loops, balancing loops, which are all pulling away from variables that are involved in this giant growth loop. And so it's another example where we get saturation effects. So this is like a limited growth model. So here I've written it out. The sales growth positive feedback loop would cause all participating variables to grow without bound if it were not for at least one of these other three loops. Together, they cause the initial growth to saturate, as in most cases when a reinforcing loop is followed by a balancing loop. So we recognized reinforcing followed by balancing loops. Okay. The other question, draw an example behavior over time plot for annual revenues. So annual revenues is participating in this giant sales growth loop. So we imagine it's going to initially grow, but its growth is going to be reduced by these saturation effects and hiring controlled departures and saturation. So we would expect an S-shaped curve with fast initial growth and then saturation. Notice on this curve, I've labeled time on this axis, and I have given myself a label for the whole graph here, which I could have also put on this axis here. So it's clear that I'm talking about annual revenues and not any other variable. I've even given myself units, which is great. And then I've also then made it clear that this is time, and the time is in years. And so on the midterm, make sure if I ask you to draw any graphs like these, that you're very clear to label as much as you can to make it clear what you're talking about in the graph. Okay, next problem. Explain the error in this attempt at a stock and flow diagram. This almost looks like a stock and flow diagram. So I have to say, what is wrong with this? So the stock looks fine. There's a flow coming out of the stock. That looks fine. This stock has a causal link to the flow. That seems reasonable. But then there's this converter over here, and that's where the problem comes into play. There's a flow drawn directly into a converter. Flows can only interact this way into stocks. They can come out of stocks, and they can go into stocks. Converters can have these causal links, just like this one here, interacting with flows, but flows cannot go directly into converters. So this is a nonsensical stock and flow diagram. Next problem. Explain the error in this stock and flow diagram. I've got two stocks. They both are interacting with flows, so this flow is going out and coming in, and that looks fine. Causal link going into this flow, that looks fine. Causal link going out into the converter, that looks fine. But then the problem seems to be that this converter directly interfaces with stock number 2 via a causal link. And the only way you can change, or the only way you can modify stocks is through these flows. So you can imagine the converter might have a causal link up to the flow, but not directly to the stock. There's only a one weird exception to this if you wanted to somehow make your converters drive the initial conditions, but that is in a sort of an advanced case. So in all of the sort of examples that we'll do in this class, if you've got a converter or a dynamic variable like this that is not a stock, or really any dynamic variable, you cannot draw one of these thin links to a stock. The only way you can make an impact on a stock is indirectly by making an impact on the flow connected to it. All right, now a causal loop diagram. So I've given you this causal loop diagram. It's a partial CLD, but I haven't labeled any of the links. And so I'm just asking you to label the links. The context here is I'm modeling how an employee responds to signals from their salary. And so in this conceptual model, the employee's effort devoted to a job depends upon their satisfaction with their current salary. So the employee has some desired salary, and that modulates their job effort, and their job effort helps modulate their actual salary. And I'm claiming that all these things are going to participate in a negative feedback. So how might that work? Well, if you increase the desired salary, so you want to make more, then you think you might want to increase the amount of effort that you put into your job. Now, if you increase the effort you put into your job, if the world is fair, then you'll actually get an increase in your salary. But as your increase in your salary comes closer to your desired salary, that may end up causing you to decrease your effort at the job because you don't want to work more than you need to. And if you're already making the amount of money you need, then you can reduce your effort. Your effort still stays high, it just doesn't further increase. And so these are the labels I was expecting. So there's a plus here, if you can't see it because it's kind of cut off a little bit, a plus on this link down here, and then a minus on this link. And so this plus and this minus are what participate in this negative feedback loop. All right, so we're almost getting done here. So 11 here, another CLD problem. These are three very simple CLDs, but only one of them represents a causal relationship in a straightforward way. So we want to select the best example of a CLD. In this first one, increase in expectations, we say has a positive causal relationship on decrease in happiness. The problem here is we put verbs in these things. So it's hard to create a scenario where you say, well, what is the increase in my increase in expectations, and how would that change the decrease in happiness? So if I increase the increase, does it decrease the decrease or increase the decrease? So it just doesn't make sense. And so we like to get rid of those verbs. And then so down here, dry roads and hot weather, well, those are both nice noun phrases. Roads and weather, and they'd be modified by adjectives, but they're still noun phrases. And it does happen to be that when you have hot weather, you also typically have dry roads. But the problem in this one is that the causation is flipped. So it's not that dry roads cause hot weather, even though they're correlated together. If anything, hot weather causes dry roads. And so this arrow should probably be pointed back the other way. So the only one we're left with is this one. So expectations, happiness, those are two nouns. And this is, what's being modeled here is if your expectations go up. So if you have really high expectations, then this is modeling that you might have low happiness because you're always disappointed because your expectations are high. So if you increase your expectations, you might decrease your happiness because those expectations won't be met. Likewise, if you lower your expectations, you might increase your happiness. And so that's why there's a minus here. So that's the one we're selecting as the correct answer. All right, the last problem, so the most kind of advanced problem or complicated problem here probably, is we've given you this differential equation system. So there's a two-compartment differential equation. Here dx dt equals minus x minus y, and dy dt is just equal to x minus y. So we want to draw a stock and flow diagram that represents it, decide whether the feedback in the first equation is negative or positive, and then draw a simple CLD representing the relationship between x and y, and then label all the links and loops. So the first part, draw the simple stock and flow diagram. Well, you could draw this in different sorts of ways. You certainly could draw dx dt as one dynamic variable. You could even call it flow into x, and you could call this flow into y. And you could talk about how flow into x has a relationship with x, a negative relationship with x, and a positive relationship with y, and vice versa for flow into y. Or instead of all of that complicated stuff, I could just recognize that x minus y shows up in both. So I'm going to draw x and y as my state variables here, and a single flow rather than two flows. And so they're sharing the same flow. So rather than having x out here with a flow into x and y somewhere else with a flow into y, and then a coordinating network working between them, instead I just drew an x and a y, and the outflow of x is the inflow of y, and that outflow is x minus y. And so that's what we end up getting here. So like I said, there are other ways you could have drawn this, but that is a simple way that, to simplify this when you notice that you've got a quantity that shows up in multiple places. All right, so then the next step, what type of feedback is represented in this first equation here? Well, if I look at the first equation, I can see it's got a dx dt. I can also see it as an x, and so now I can ask, that's the only feedback that's in the first equation because y is just this outside variable, so the only possible feedback is here. So then I can ask, how do these two things relate? Well, the dx dt always has a positive link with x. So the flow corresponding to a certain state variable always has the inflow for a certain state variable has always got this sort of positive relationship. So yeah, so how does x change when dx dt increases? Well, it increases. So that's where this positive comes from. Now I use the formula to get the other link. So here I see that via this formula, x, because of this negative out front here, if I were to increase x, it's going to make dx dt more negative. So the change in x will become more negative. So x will be more likely to shrink when x is large, and it will be less likely to shrink when x is small. So there's an opposite relationship going on there. So when I look at those two things together, I see I get a negative feedback loop, and so that's why the answer to this one is negative. All right, last portion of that. Draw a simple CLD representing the relationship between x and y. Be sure to label all links and loops. Well, going back to from part A, we said that this was a decent enough stock and flow diagram for this. And it just created an intermediate flow, which was equal to this x minus y. Well, I can do the same thing with the causal loop diagram, recognizing that there's a feedback loop here as well as a feedback loop here. And so I've got x out here and y down here, and this flow, which you can think like x minus y. Well, x has a positive impact on x minus y, but then x minus y, because of the dx dt equaling negative x minus y, has a negative relationship. That's what's going on here. Similarly, x minus y, well, x minus y by this equation, if x minus y increases, it has a positive relationship on y. But by the formula x minus y, due to the minus y, if y increases, x minus y decreases. So there's a negative relationship. So we see two coupled negative feedback loops, and that's the causal loop diagram that we're shooting for here. All right. So those are the kind of practiced midterm examples. I also think these will be helpful if for studying for the final exam as well. If you have any further questions, again, feel free to contact me or the TA, either in person, over Canvas, or by email, and take a look at some of the other resources we have for studying for the midterm and the other exams in the class on Canvas.